Hi, this is Mrs. Spradling, and you are going to be taking notes over Newton's second law of motion, which we call the law of force and acceleration. So if you will please add to your table of contents in your journal the second law, law of force and acceleration, and then we are going to turn to that area in our journal, and I would like you to copy down all of these bullets here. Remember, you may pause the presentation at any time so that you can take notes and then pay close attention when I'm explaining the law. So Newton's laws of motion, the second law is very similar to what we studied with how unbalanced forces change the speed and direction of an object's motion. Remember, what's the definition of something when it's an object's speed or an object's direction changes? That term we learned was acceleration. So there is a relationship between the amount of force we put on an object and how that object will accelerate. So the big idea is the greater the force you put on an object, obviously, the greater the object will accelerate or move. Now, if you have something with a greater mass, more massive, you're going to need a much larger force to get the same or equal acceleration. So you will often see Newton's second law of motion shown with this formula, which we will be doing calculations with. And that is force, which force is going to be in kilograms, is equal to the mass of an object. Oh, I'm sorry, I messed that up. Force is not in kilograms. We measure force in newtons. Mass we measure in kilograms, and the accelerations units are in meters per second squared. So those are the units that can help you figure out in a problem how to use this equation. So we're going to look at this example that we have here. Let me take and erase my little notes. We have this car, the blue car down below, you will note, has a mass of 1,000 kilograms. We want it to accelerate at 0.05 meters per second squared. So, in order to do that, if you use this formula, you're going to multiply 1,000 times 0.05. Now that's very easy to do. You just simply move your decimal over the number of zeros to the right since we're multiplying 1, 2, 3. So my answer would be 50 newtons of force in order to get this car to accelerate at 0.05 meters per second squared. Now, we've got a much larger car now. How many newtons of force do you think it would take to get this van to accelerate the same acceleration? You should note here that our mass is exactly doubled. So with that, what do you think would happen with our answer? Well, 0.05 times 2,000, when we multiply, we get 10, and we have to move our decimal over 2 places. So our answer is 100 newtons. And in fact, it would take double the force to get the same acceleration when your mass is doubled. So some examples of Newton's second law. I would like you to copy just 2 examples here that really make you understand what's happening. You can choose any 2. First of all, hitting a baseball, the harder that you hit the ball, the faster the ball is going to go. When you accelerate or decelerate a car, you might want to think more along the lines of a bicycle. The faster you pedal your bike, the faster you're going to go. Also, decelerating, the harder you squeeze on the brakes, the faster you will stop. Positioning of football players. Think about this. The more massive players, if they have more mass, they're on the line because they're very hard to move because they're more massive. You need a lot of force. Where in the backfield, If you've got really, really fast players in the open, they're hard to slow down because they have a lot of acceleration. So their force, you need a lot of force to stop those players. So positioning in football is important. And then also you think about a loaded versus an unloaded truck, or maybe an 18-wheeler versus a little VW Bug. You're going to have more force in the engine in a big truck versus a small car.